did you get all that stuff?
I sure did. Thank you for sending it.
I cannot hear you.
Oh.
There you go.
Okay.
Did you get it? It was on my end. Did you get it?
Yes, I did get it. Thank you.
Did it work?
Yes, I think so. I only looked at one of them, so.
I always like to know when those things work. Okay, good. Okay, so today we're going to continue back into Chapter 9. I'll kind of review a little bit what I talked about in a lesson I wanted you guys to see yesterday. Let me talk about, I told you guys I lied to you, and it wasn't Dr. Page's fault at all. He's being told by his bosses. But I told you we were absolutely, definitely, for sure going to come back hybrid next week. And that's the thing I think that the people over Dr. Page had told Dr. Page. And then, of course, the news comes yesterday that that's not going to be the case. And we're going to do remote a couple more weeks. We're just going to keep grinding away. And again, I guess the thing is I always like to just see you and have those interactions. But if we're on remote, we're just going to do remote. We can go a little bit faster on remote. So today we're going to continue in Chapter 9. A couple things, I need to go change my calendar if you guys look at the calendar. But I'm going to make your quiz due, because I was saying I was going to make your quiz due when I saw you guys on Monday, Tuesday. But I'm going to make it due on Wednesday. So the quiz on Chapter 8, 9 on Wednesday. We're going to Google Meet today. We will Google Meet again tomorrow from 9 to 9:30. I think we're going to be, we'll see. We're going to be close to done with Chapter 9. I think there's a lab/activity that I always do with Chapter 9, and it's just building molecules. And this year, I think I'll talk about this more probably tomorrow, maybe on Tuesday. It's called the Tinker Toy Lab, and it's one that you're just going to have to do without building, and I'll kind of help you with that. And so you've already turned in the lab, the brass lab, which I still haven't finished grading. You're going to have the quiz, will be grade number 2, and then that Tinker Toy Lab, and we're going to move into Chapter 10. And I'm really hoping, and I have no idea. I was just talking to Mr. Hodis is why I was late about what's going to happen next. But hopefully you'll be here in person for the Chapter 10 test, or the 8, 9, 10 test. So anyways, we're just going to see how it goes. Okay, so let me just go back real quick to Chapter 9. Again, we're only going to cover half of Chapter 9, like I said, in the part that is going to pertain to the AP test. And so that's what we're going to focus in on. Okay, so let me just, the problems for Chapter 9. So things you guys can be working on now are the quiz, and you can be working on the problems from Chapter 9. You can be working on the problems for Chapter 8 still. And like I said, I'll get you, and I might even do it tomorrow. Maybe I'll get this Tinker Toy Lab up on both Canvas and my website. So there's a lot of things you guys can be working on. Okay, so back to, and again, I think we talked about this, but real quick, here are the problems for Chapter 9. So if you didn't note these the other day, you should note these. So again, these are things that you guys can be working on outside of class. So you got the Chapter 8 problems, you got the review for 8 and 9, you got the quiz for 8 and 9, now you got problems for Chapter 9. And like I said, maybe I'll even do it tomorrow. We'll just see. We'll see how far we get today in terms of this lab/activity that goes with Chapter 8, 9. Okay, so those problems, I've talked about this. And then yesterday in the notes, I talked about this, and I wanted to just again, and I know in the notes I went over that, and I don't know how many of you watched the notes. Let me just talk about this for a second. What we're always getting into in this chapter is we are getting into explaining how dots work, how the dots work, and you're going to see that here in a minute. But there's 2 theories out there. Theory 1 is the one that we are going to need to know. This is the one, and to me it makes sense, and you'll see that hopefully today a little bit. It's called the valence bond theory. I think of James Bond, the valence bond theory. And it's also called the localized electron model. So the valence bond theory or the localized electrons. And this is how this works. If here is atom number 1, and here is atom number 2, and here's the electrons are always in here. And that the word that they use in chemistry is the electrons are localized. They're localized. They're in a specific spot between the two nuclei of the atom. This is the theory we are going to use. That's why I start. This is the one that we're going to learn about. And again, we're not going to have any kind of math or calculations here at all. This is just going to be, again, it's going to go back to, I'm going to go back again today in class to the left side of the board. And we left that column hybridization open, and we're going to fill a lot of that in. Now, theory 2, which is the theory, which is the second part of the chapter, and actually in a normal year, I don't get to theory 2 either, just because it's in a normal year. We really gotta bust our tail to get through everything. And this year, of course, being different, but it's called this. So we're not going to cover this theory. We will not do this. It is called the molecular orbital theory. And I don't know if it's hard. It's something that if you guys took chemistry past our class, you guys would get into. And if you care to, you can look at both the notes I've got posted online, and you could read the second part of chapter 9. I'm not going to hold you to it. The AP test isn't going to hold you to it. But what this says, so if here's atom number 1 and here's atom number 2, what the deal is here is the electrons are out here. The electrons are outside the atom. And so they are called delocalized. So this theory, again, is called either the molecular orbital theory or the delocalized electron theory. And again, this we're not going to come to. And again, if you took chemistry beyond our class, you guys would come to this. But this is the theory that we are going to learn about. Okay, and kind of I've got the board here. So anyways, kind of the big picture of what is going on. So, and again, I talked about this in the video that I posted for yesterday. But what this model says, this localized model, let's say we're talking about the bonding in HF. So I'm going to go back to the dots and electron configuration. So HF, so if I've got H, and its electron configuration is 1s1, which means we've got one orbital, a 1s orbital with a single electron in it. And then if I've got fluorine, its electron configuration is 1s2, 2s2, 2p5. It's like this. And so if I do, again, the orbital diagram, so here's the 1s, so here's the 2s, and then here's the 2p's. And so 1, 2, 3, 4, 5, and it's like this. And so if you remember the dots, now again, to me, what we're doing here is we're really explaining how the dots work. So we go back to doing the dots. So I've got H, and then I've got F, and we pair up the single dots. Well, that's what's going on here. These half-filled orbitals are what are bonding. Okay, so that's kind of what that valence bond theory, the localized electron theory is these paired up dots. This single dot was that 2p orbital with a single electron, and then this single dot was that 1s orbital with a single electron. So that's kind of, to me, the idea behind this. Okay, so then back, and again, I went over this yesterday in the notes, and you guys could see it. It's posted online, and I don't want to spend a lot of time, but I did want to go over that again quickly. And you can see here in this diagram on the bottom of the page, same thing. So in hydrogen, a 1s1 and a 1s1, so two half-filled orbitals, and they combine. Then here is again the same thing. So, and again, I went over this yesterday, but if we have F2, so we have 1s2, 2s2, 2p5, so we have a half-filled orbital, just like it shows there at the top. In both of the F's, well, those combine, and that's where the bonding comes from. So F2 according to the valence bond theory, and then here is HCl. And again, I went over yesterday online, and you can look at that that, and you can see that. Then where it kind of gets tricky though is here, and there's a lot on this page that I want to talk about, but let me try and just diagram some things on the board. To me, where this gets tricky is with carbon. Okay, so if we're going to do methane, so CH4. So again, what we're doing is we're trying to explain the dots. So if I've got CH4, now guys have been over a year and a half now in chemistry, so you guys have done dots quite a bit. So if we just go back and do dots the way that you guys learned in first year chem, we had a carbon with 4 single dots, and then we had the H's here. Okay, and this my students in first year chem are going to be doing probably in a month or 6 weeks. But if I go back to explaining, well, what's going on here? Well, carbon is this, 1s2, 2s2, 2p2. So it looks like this. So here's the 1s, here's the 2s, and here's the 2p. And this is where the model has to be explained a little bit. So the 2p's would have, the first two would have 1 electron, or be half filled, and then the third 2p orbital would be empty. And then we've got the 4 H's, so 1s1, so I'm going to write 4 H's. And again, I tried to talk about this online, but this to me is kind of gets into the core of what we're trying to do, what this chapter is trying to explain. Well, if you look at this, and we go back at the dot structure of carbon, we have 4 single dots, where it appears to me like carbon should be like this. That's the way it should be. It's got a pair, here's the 2s, and then 2 singles. And so the explanation, the theory that this model says is this thing called hybridization. And so what happens in this is one of these 2s electrons, to explain why carbon is correctly written with 4 single dots, not like this, is one of these 2s electron is promoted to here. And so what we get then in carbon, this is what the theory says, is here's carbon, so here's the 1s, which hasn't been touched. So the inner core electrons haven't been touched. And the single s and the 3p, they hybridize. Hybridize is a key word in this chapter. And I said this yesterday, and the best example that I've got is a hybrid is a cross. It's a cross between two things. And so I play golf. I actually played golf even yesterday. Yesterday afternoon, I played golf. I didn't play very well, but I played. It was nice to be able to play golf. But in golf, there's a great example of a hybrid club. And those that play golf would know that. It's a club that is, it's kind of like a wood, and it's kind of like an iron. It's a cross between the two. And that's what happens here, is these hybridize, and they become one orbital, one kind of orbital. And they are called, in this case, they're called Sp3. The S, because it's an S, and the P, and there's 3 of them, and so they hybridize. And again, one was promoted, and so what we have then is we have 4 single orbitals in this Sp3 hybridized orbital. And that's what we're going to have to predict in this chapter, is the main thing is hybridization. And to me, and of course I've done this many, many times, but it goes back to electron domains, and I'll show you that. But now that I've got this, so now I've got carbon with 4 single dots. So there it is, 1, 2, 3, 4, and then we're going to pair up here, 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 and here, and that's exactly what happens. So the hybridization in CH4 is this. Okay, so we go back and we say the shape. Well, we do the dots. Go back to chapter 8. We count the electron domains, 1, 2, 3, 4. So there's 4. So the shape of this is tetrahedral. The bond angle is 109.5, and the hybridization is Sp3. So if we go back here now to what this table that we were working on in chapter 8. So we go back to this table now, and we left this column right here. And so at 4 electron domains, tetrahedral, CH4 nonpolar, the hybridization here is sp3. So this table, and again, I was hoping to have this up next week, and of course you're not going to be here. So again, if at some point, if you haven't got a picture of this, you should. And what we're going to learn here in just the next couple slides is if you guys can see, let me, as you don't know, not sure what you can see, but the ones that are 4 electron domains, so the tetrahedral, the pyramid, and the bent, their hybridization, all of them are going to be sp3. I'm going to explain that, but that's what this model is saying. Okay, and again, it's just a model. This is just a theory about what is going on there. Okay, so the hybridization for 4 electron domains, in other words, explaining the dots. How are the dots working? Is sp3. Okay, so then let's go on to the other the other shapes and bond angles that fit into that group. Okay, so back. So to me, it always starts with doing the dots, counting the electron domains, and that tells me really the family or the grouping this goes into. And if you look here, again, there's a lot, it's kind of overwhelming on this page. But if you look at the top right-hand section, it's what I was saying. So there's 1s2, 2s2, 2p2, and that's where it says carbon in the ground state electron, but then carbon in the excited state, and then right underneath it is that hybridization thing. One other thing here that I should write for those of you that are listening to me is what happens to the shape, is we know S's are spherical. S's are spherical. And p orbitals are dumbbell or hourglass shape. Well, when they hybridize, when they cross, they kind of have a little node from the S, and then they have the big nodule from the P. And so this is what the sp3 orbital looks like. This is what the model says. And again, what an orbital is, going back to what we talked about in chapter 7, an orbital is a region in space where electrons are found. And so somewhere in that cloud is where those electrons are. But that is the shape of those orbitals. Okay, so then again, so there's kind of a little bit of information overload on that page there. But anyways, that's kind of showing. And then the actual shapes I was trying to explain. So if you look on the left side, the second one down with the blue, those are the ones that are those sp3s. Okay, and then here is again another illustration of this. So there's 4, look at the left, 4 carbon sp3. Now this I did not get to yesterday, but it's kind of a continuation of what I was just talking about. So 4 carbon sp3 hybrid orbitals, 4 hydrogen 1s atomic orbitals, and you can see again localized electrons, so the electrons between the 2 nuclei, and kind of how that would look. And notice what it says too on the bottom. So molecules with an AB4 or 4 electron domains. It doesn't say that, but you should note that. So molecules with an AB4 tetrahedral or tetrahedral derivative shape are sp3 hybridized. Or you can say anything, and we'll look at the others here in a second. Anything that has 4 electron domains is going to be sp3 hybridized. Okay, and I'm just going to, this again is just kind of showing the shape of the sp3 with the kind of the S, the little circle, and then the P, kind of the big lobe. Okay, now, so NH3. So what happens in NH3? And this one's a little bit more confusing, but what you need to remember, do the dots, count the electron domains, and that's going to tell you the hybridization. So the hybridization of CH4 and NH3 So because it's going to be 4 electron domains again, it's going to be sp3 hybridized. So let me, if you're writing things down here or taking a picture of this slide, and I'm going to write some stuff on the board here. So again, just trying to really what we're trying to do here. Whoops, I went a page. Is I'm trying to explain the dots. Is what I'm trying to do. So if I'm doing NH3, so again, if we do the dots, so I've got 5 valence electrons here, and then 1 times 3 is 3, so I get 8 valence electrons. And NH3, N is like this, and so I put the H's around it. And H, technically, remember, is the exception, and it's the one exception we use over and over and over again. It only needs 2 electrons, so it is fine. But the N, I need to fill in its octet, so I do that. I've got 2, 4, 6, 8, so I'm good. But now, again, we're explaining the dots. We're explaining what happened. Well, if I go back to N, and again, I do the electron configuration. I got 1s2, 2s2, 2p3. And H, I've got 1s1. And in this one, this is why this one's a little bit confusing. You could go, well, if I go back and I do my orbital diagram, so I'm here, and here's this, and then I got the 3 2p's. Slow down here. So there's 1s2, 2s2, 2p3, and then the 1s1. And you look at this and you go, okay, this one I understand. This one I see, because again, what we're doing is we're pairing up the single dots. So we pair up here, here, and here, 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 and here. But to be consistent with the model that we had with carbon, we're going to, again, use that idea of hybridization, that these are going to hybridize. And because, okay, so I go back, count, I did the dots, count the electron domains, 1, 2, 3, 4. So this is, again, going to be sp3 hybridized. So these hybridize. And so what I get, instead of a single S and 3 Ps, I get 4 sp3 hybridized orbitals. That's the hybridization here, again. So if I count, do the dots, count the electron domains, that's going to tell me the hybridization. But in this, again, I have this, and then I have these singles. And then it pairs up, again, with those single dots, so it pairs up here, here, and here, and that's where the localized electrons are. And so if you look, again, if you look at N, here's N, so it had single dot, single dot, single dot paired up, and then it has a non-bonded pair. And that is why when we came back here, again, we do the same idea. What I'm trying to say is the same process. Do the dots, count the electron domains. So we're doing this one right here, right now. So we're doing AB3E, 4 electron domains. That's what I had over there. Trigonal, pyramidal. It's less than 109.5. NH3 polar, but its hybridization will be sp3. And the same is going to be with the next one I do, so water. So to be consistent with the model, we got to, even though really NH3 and the next one we're going to do water, we really don't need this concept of hybridization, but to be consistent across the board, that's how we would explain the hybridization, explain the bonding, explain how the dots work. So we just did this slide. Okay, so here's water. So water, again, to do the dots, so there's water. But again, when we do water, and I'll do it on the board here in a second, if we do the dots and count the dots, you would see it has 4 electron domains. Okay, so for water, so I'm just being consistent in what I'm doing. So for water, so again, if I do the dots, so I have 2 plus 6, so I have 8 total dots. Okay, so I have oxygen and then the 2 hydrogens like this. I fill the octets. Hydrogen is fine the way it is, and if I count 2, 4, 6, 8, so I have 8, which is good. But now how does this work? With this model? And again, if I go back electron domains, 1, 2, 3, 4, so this is on that tetrahedral, the 109.5 bond angle, be a little less than 109.5 because of the non-bonded pair. The shape here is bent, but how does the bonding work? So I've got oxygen, which is 1s2, 2s2, 2p4. So in an orbital diagram, it looks like this. And then the 2 p's are like this. I've got 1 that's filled, and then I've got 2 that have a single. And then I have the H's, which is 1s1. Sometimes I get moving too fast and I need to slow down. But again, to be consistent, just like with NH3, you could look at this and you go, okay, this kind of makes sense. You know, we could just pair up here and here, pair up those single dots, and then the non-bonded pairs here and here. But to be consistent with the model, again, we're going to say instead of having a single S and 3 P's, these are going to hybridize. They're going to cross. So instead of having a single S and 3 P's, we're going to have 4 equivalent Sp3 hybridized orbitals. And 2 of them are completely filled, and the other 2 have a single. And so it would bond like that and that. Okay, but what you need to know, okay, you do the dots, you count the electron domains. If there's 4 electron domains, the hybridization is Sp3 hybridized. So that means a single S hybridizes with the P's. Okay, now on to the next kind of hybridization. Okay, so Sp2 hybridized, so boron. And this is going to go with anything that has 3 electron domains. So I'm going to give you guys a second for those that want to write this down. Again, I'm going back and forth and making everybody dizzy, but I kind of want to write this on the board and explain what's going on here. So trigonal planar molecules, or molecules you might want to know that have 3 electron domains, AB3, they are Sp2 hybridization scheme. Okay, so and I'll come back to that, but let me show you what I'm talking about here. So I'll go back over here, but the example we used was BF3. BF3, so I'm just going to use BF3. So in boron, so we know the dots are like this. Okay. Or if we count it again, I have 3 plus 21 is 24, so 8, 16, 24. And we remember boron was one of those exceptions that only needed 6 electrons to fill its outer shell. So hydrogen only needed 2, beryllium 4, boron 6, and those were the exceptions. Okay, but now what's going on here? How does this work? Well, I've got boron, which is 1s2, 2s2, 2p1, and so here's the 1s. Here's the 2s. And then here's the 2 p's. And again, the way we do the dots with boron is we do this. We do three single dots. The way it looks like according to this is it should be like this. The pair and then the single. That's not the way it is. So it's the same idea. It's the hybridization. So what happens here is, again, what's going to hybridize are these three orbitals, not this. So this is going to promote, and these are going to hybridize. And so what we're going to get then is this. So here's the 1s. And then we're going to have these three equivalent hybridized. And this is going to be called Sp2. The 2 because there's 2 p's. And we're going to have 3 single electrons. So 1 here, 1 was promoted, and that one. So this one went there. So 1, 2, 3. And then we've got a p orbital that's not hybridized, but it's empty. So that's the way, again, when we have 3 electron domains. And then if I did fluorine, remember, is 2p5. So I'd have, in fluorine, I have like this. And I have 3 of them. So if I have 3 fluorines, and then another one here. And so, again, so we're just going to pair up the single dot, so it's going to bond here, here, and here. And that's where we get these bonds, these localized electrons. Okay, so 3 electron domains. So if I go back here, and I go over here to, I don't know if you guys can see this or not, but if I've got these 2 that are 3 electron domains, so their bond angle is 120 or less than 120, so it's going to be the triangle, which BF3 is, or bent. Here were the examples, but the hybridization for both, so this column right here for both, will be Sp2. So you guys are way smarter than me, but this is how I remember this. The superscript number is telling me how many p orbitals that hybridize in this group. That's how I do this. And then if I go back here to kind of the family that they're in, if it's AB3, there's always, in the SP, there's always 1 less. The number is always 1 less. So if it's AB3, it would be Sp2. So if it's AB4, it would be Sp3. So the number is always 1 less. So if that's the case, what's going to happen here? AB2, we'll talk about that. The number would be 1 less. It'll be Sp. So again, this is why this is all connected. And these really, chapters 8 and 9, to me, go together very, very well. And that's why we'll just do these as one chapter. Okay, so do the dots, count the electron domains. If the electron domains, if there's 4 electron domains, then the hybridization is Sp2. I'm sorry, hybridization is Sp3. 4 electron domains, hybridization Sp3. If there's 3 electron domains, the hybridization is Sp2. Okay, we kind of got ahead to the next one. Okay, so trigonal planar molecules, this is a slide that was just up. They have Sp2 hybridization. Okay, and then what I was just talking about, so then in beryllium or linear molecules, they're going to have Sp hybridization. Okay, so hopefully kind of, I don't know if I'm doing a very good job of explaining this or not, but just how this works. But again, so what it says there on the right, linear AB2 molecules have sp hybridization schemes. So in other words, it doesn't say it on this slide, if there's two electron domains, it's going to be sp hybridized. And you can see there on the top kind of what happens here. So if I try and explain this, so if I go back here, so the example we used was BeCl2. So for BeCl2, so again, the way that we do the dots is beryllium has 2, chlorine 7 times 2 is 14. So I've got beryllium, I've got chlorine. And then if I count, and remember beryllium was one of those 3 exceptions that it only needed 4 electrons in the outer shell. So I've got 2, 4, 6, 8, 10, 12, 14. Let's see, 2, 4, 6, 8, 10, 12, 14, 16. Did I count that right? So yeah, 16. So that is right. But again, now how do the dots work? So if I have beryllium is 1s2, 2s2. So it's like this. And there's nothing in the 2p's. Nothing at all in the 2p's. So the way we really should do the beryllium, like this is the way Mr. Conyers, Mr. Hodis, and myself taught you guys to do this in first year chem, which is the correct way, which is what this localized model says. But really, it should have been like this. But again, we've got these 3 empty 2p orbitals. So what happens here then is, again, one of these promotes, and then these 2 hybridize. Again, they hybridize, they cross, they become 1 orbital. So what you really get here is you get the 1s. So you have the 1s, which didn't change. But then these 2 hybridize. And this is why it's sp, only 1p. And in this case, they got in both singles. And then we have these p's, which did not hybridize. So just like in sp2 hybridization, we had 3 sp2 hybridized orbitals, 3 equivalent sp2, and 1 empty p. Well, here we have these 2 empty p's, but that's why this is correct. And then if BeCl2, so Cl ends as 3p5. So if I look at just those p5s, okay, and I had 2 of them. And so it's going to bond there. So a lot of drawn lines there.
Mr. Wood,
Yes.
for those empty p orbitals, will we ever use those when?
I don't think so. Mason. We're going to talk about tomorrow. We're going to talk about what happens with double bonds and triple bonds.
Okay.
I don't think we're going to come to that. Great question. Okay, so then if I go back here now, so if there's 2 electron domains, so if I go back here to right up here, so if there's 2 electron domains, linear 180 degrees, well then over here, the hybridization now is sp. And to me, I always kind of think this model is kind of cool. Like I said, from the little bit of reading I've done, I guess that other model that we're not going to get to really explains other things a little bit better than this model does. But to me, this is explaining some of the things with the dots and how bonding works and the available places for electrons to bond. Okay. So again, if you can see here, so, and again, they at the top, they kind of diagram what I explained, and then they're showing what is going on. Okay, so here are the steps. Steps to determine hybridization is do the dots, determine the shape, specify the hybrid orbitals based on the electron domains. So if we have 4 electron domains, the hybridization is going to be sp3. If we have 3 electron domains, it's going to be sp2. If we have 2, it's going to be sp. What I would like you to do, we've got about, I don't know, 6, 7 minutes left. I'd like you on these 3, so pf3, SO3 negative 2, and NH2 negative, I would like you to do the dots to tell me the shape, the bond angle, and the hybridization. So let's take, I'm just going to give you guys a couple minutes, and I'm going to do them all on the board, and then we will stop there for today. So see if you can do, again, you're going to do the dots, you're going to name the shape, you're going to tell me the bond angle, and now you're going to tell me the hybridization. And really, you should tell me, is this going to be a polar or non-polar molecule? So we're doing the dots, the shape, the bond angle, polar, non-polar, and now the hybridization. Okay, so let me go through these. So PF3, so I get 5 plus 7 times 3, so I get 26 dots. I'm sorry, I get 21 dots. 26 total dots. Then I got P in the middle. Fluorines around it. Hi, Michelle. Fill the octets. Count 8, 16, 24, 26. Good. So then if I count the electron domains, a non-bonded pair is 1, 2, 3, 4. So this has 4 electron domains. So with 4 electron domains and 1 non-bonded pair, the shape of this is pyramidal. The bond angle at 4 electron domains with the base shape being tetrahedral is 109.5, but because of this non-bonded pair, it takes up a little bit more room. So the bond angle would be less than 109.5. That's all you need to say. You wouldn't need to give me a number, just less than 109.5. This would be polar because of these F's. That shape is polar, and because F is one of those molecules or one of those elements, one of those 4 elements that is.
All right, guys, what is the atomic number for lithium?
You should know that.
You paying attention?
Everybody's asleep.
3.
What is it?
3.
3.
Yay!
There you go. I got it. And so now what we learned today is the hybridization then with 4 electron domains of the Sp3. The Sp3. Okay, I think I'm out of time. So tomorrow where I'm going to start then is with SO3 -2. So I'll start there tomorrow. So tomorrow we'll meet at 9 o'clock. And I think that's it. Any questions you guys have? Okay. I think that's time. I think it was 24. Okay, guys. Hey, have a good day. I'll see you guys tomorrow. We'll Google Meet again.
Thank
Thank
you. Mr.
you.
Smith.
Thank you.